All right. Hi, everybody. I hope you're doing well this morning. I have progressively gotten more sick, so to save you from my germs, I am going to stay home today. But I'm recording a lesson for you so that you can still learn without me and pretend I'm right here in the front of the room. So, today, let me get my lesson on the board for you. There we go. Today we are starting our new unit. So on your desk, you should have a notes packet and an assignment sheet. It's on a purple sheet of paper. Go ahead and flip that over. On the back, I have a summary of how to graph rational functions on there for you step by step. So anytime you're doing anything in this unit, you should have this purple paper on your desk and flip it over so we can follow the steps. Today, we're going to graph rational functions. So you just took your test on polynomials. Polynomials are smooth, continuous graphs, so they are pretty. Okay, rational functions means you have to have a fraction with a variable in the numerator and a variable in the denominator. So basically, you have this ugly fraction with x's on the top and the bottom. You probably remember the worst day of your life was in third grade when your teacher introduced fractions to you and you were like, what the heck is this? Why do I need to know this? It's the same for pre-calc. Okay, these fractions make really funky graphs. So we're going to learn how to make these really funky graphs without our calculator today, step by step, and learn all of the math processes behind finding the graph of this rational function. So we're going to start off just by taking notes on everything that could possibly happen as we're graphing our rational function. We can calibrate our square point before we start. So as you can see at the top, it says a rational function is in the form of this. Okay, that just means that you have x's on the top of your fraction and x's on the bottom of your fraction. That is a rational function. Anything that has a fraction with letters in it. So, the first thing that could happen that's funky in a rational function is our graph could have a hole in it. So if you look at your purple sheet, step one for solving rational functions is we always have to factor first. So for example one right here, which part of that do you think you can factor? You're right, you can factor the top. So if you look at the top of that function, that's x squared minus 1, we can factor that by difference of squares, which I just call the square root method. So if you square root both of those pieces, you would get x plus 1, x minus 1. That's how you factor that. So the top of my function is going to be parenthesis x plus 1 and parenthesis x minus 1. The bottom doesn't factor, so you're going to copy it down exactly the same. You probably have nightmares from this from Algebra 2. But right here, this is my favorite part, those x plus 1s cancel. They are exactly the same parenthesis, so they will cancel out. Whenever you have something that cancels, it makes a hole in your graph. So a hole in your graph is like an open circle. I don't know if you've ever seen a graph like that before, but that's what we're going to graph today. So that open circle is what a hole in the graph looks like. Our hole is going to be located at whatever cancels out. We have to set that equal to 0, just like we do when we find zeros of functions. So our hole is going to be located wherever x plus 1 is equal to 0, because that's what canceled. So really, our hole is located at x equals negative 1. However, if it's a point on a graph, I not only need an x value, I also need a y value as well. So it's really cool that I know x equals 1, or negative 1, but my answer should be an ordered pair, an x and a y. So in order to get our y value, we're going to have to take that negative 1 and substitute it for x. Now, because this canceled out, the only part of your function that you have left over is y equals from the front, x minus 1. That's my new, beautiful, pretty function after that hole canceled out. In order to get the y value of the hole, you need to take this x value and substitute it into your new pretty function. So when I substitute that in, I'm going to have y equals parenthesis -1, substituting, we always use parentheses, minus 1. -1 minus 1 is -2. So your whole of your graph is located at -1, -2. And that's literally the first step in finding anything with rational functions. Just step 1. So let's try that again. So if we want to find the whole in the graph, we need to start, what do we always do first? If you look at your purple sheet, it says factor. So up here we can factor the top. There's a leading coefficient of 1. So when you go to factor that, you just need to find the numbers that multiply to be 8 and add to be 6. That is fast factoring because your leading coefficient is 1. So when I factor this, think about what numbers multiply to be 8 and add to be 6. You're right, it's 4 and 2. Those are the magic numbers that will help us factor. So when we factor this, it will be x plus 4, x plus 2. On the bottom, you can't factor that, so you're just going to copy that over. You have an x plus 2. Oh my god, what happens? They cancel. Whenever something cancels, that's a hole in your graph. But you have to take whatever you canceled out and set it equal to 0 to find the x value of the whole. So remember, our whole is an ordered pair. So to find the x value, set what cancels equal to 0 and solve. So I get x equals -2 after I subtract -2, or subtract 2 from both sides. So -2 is my x value, but that's not good enough. How am I supposed to know where the point goes if I don't know what the x and y value are? So I'm going to take that -2, and I'm going to substitute it into my new formula. What is my new formula once I cancel all of that stuff out? It's y equals just that x plus 4. That's the only thing that's left over. So take your -2 and substitute it in for x to find the y value of the whole. So it will be y equals -2 for x plus 4. -2 plus 4 is 2. That's your final answer. What did you just find? You found the hole in the graph. The hole is created by whatever cancels out. So that's the first funky thing that could happen in a rational graph. The second funky thing that could happen in a rational graph is we could have a vertical asymptote. A vertical asymptote looks like these pictures at the bottom, these blue lines that are up and down. This is a vertical asymptote. These are also vertical asymptotes. Okay, your vertical asymptote is created when the function is undefined. A function is undefined when you have 0 on the bottom. I don't know if you've ever heard this song, but it goes 0 on the bottom, undefined. So, if you want to find where the function is undefined, you have to take the denominator and set it equal to 0. That's how you find your vertical asymptote. So, a graph can never, ever cross a vertical asymptote because it's undefined at that location. The vertical asymptote is like a wall. You can get really close to it, but you can never cross it. You also must have a piece of the graph on either side. So see how here there's one on the left and one on the right? You must have a piece on either side of your vertical asymptote. So in order to find it, step 1 is usually factor. However, in example 1 here, nothing factors. So to find my vertical asymptote, I take what's on the bottom, the denominator, and I set it equal to 0. When I solve it, I get x equals -2, and that gives me my vertical asymptote. You're probably like, Miss Schweitzer, but we have to plug it in. You don't have to plug it in for your vertical asymptote. An asymptote isn't a point. An asymptote is a line. We need an equation of a line to graph it. I don't know if you heard this ever in Algebra 1, but there's this thing called Hoy-Bucks, and that helps us remember vertical and horizontal lines. So this is a Bucks line,
because it has an x, it has to be vertical, go crazy, and it makes a vertical asymptote. So when you solve that for x, you're done. Your vertical asymptote is located at x equals -2. We're going to do the same thing for example 2. However, this time we have to factor. So first we're going to factor. The top does not factor, so that can stay exactly the same. The bottom does factor. It has a leading coefficient of 1, so we get to do fast factor. I just need the numbers that multiply to -12 and add to 1. Just start thinking of numbers you know that multiply to be 12 that are kind of close together because they have to add to be 1. If you said 4 and -3, you are correct. Okay, that factors to x plus 4, x minus 3. If factoring is not your friend, I would strongly suggest staying after school on Monday with me. I'm going to do a factoring review session for you. Okay, so if you don't like factoring or you're terrible at it, I will see you Monday after school. After I factor that, I'm trying to find my vertical asymptote. The vertical asymptote is when the bottom is equal to 0. This time I have to do it twice, okay, because I have 2 parentheses there and nothing cancels out. I'm going to do x plus 4 equals 0 and x minus 3 equals 0. So my first vertical asymptote is at x equals -4, which look, that happened right here in this graph. Whoa, crazy. And my second vertical asymptote is located at x equals 3. Whoa, look, it's right there. That's crazy. So this picture is the picture of the function for example 2. All you know how to get so far are holes and vertical asymptotes. That's not enough, so there's got to be more stuff we have to do. So let's go to the next page. Horizontal asymptotes. So horizontal asymptotes are dotted horizontal lines, and this is the craziest thing ever. A graph can cross a horizontal asymptote because the horizontal asymptote isn't where the graph is undefined. That's the vertical. So the horizontal asymptote is just a dotted line that shapes our graph. So it will tell us when the graph is going to flatten out or what the graph is going to go towards as we're graphing it. You're allowed to cross it, which I'll show you what that looks like later. But you are allowed to cross a horizontal. You can never cross a vertical asymptote. So some of your Algebra 2 teachers might have told you a ridiculous story for finding horizontal asymptote. I'm right there with them. To find a horizontal asymptote, you must look at the highest exponent on the top and the bottom. So the only exponent we have on the top is 1. The highest exponent we have on the bottom is 2. So that graph is called bottom heavy because there are more x's on the bottom. You have an x squared on the bottom. Think of a family of celebrities that are bottom heavy. I think of the Kardashians. If you saw the Kardashians in real life, in person, you would turn to your friend and you would be like, yo, that's so cool. I just saw Kim Kardashian. So if something is bottom heavy in pre-calculus, our horizontal asymptote is yo, y equals 0. So your horizontal asymptote will be y equals 0 whenever anything is bottom heavy. Now, that should make sense because that has a y in the front, and hoi means you have a horizontal line. So y equals 0 is your horizontal asymptote. It will shape your graph, and it might be able to cross that asymptote, but we're not sure yet. If your exponents are equal, so here, if you look at your highest exponent, we have 2 and 2. They are the same. They are equal. If they're equal, we're just going to divide those numbers in the front and create our horizontal asymptote equal. So I'm going to take 3 divided by 4, which is just 3 over 4. And that's my horizontal asymptote if the exponents are equal. Now for top heavy. So if your graph is top heavy, or if your equation is top heavy, that means look at your highest exponent on the top, that's a 2. Your highest exponent on the bottom is a 1. So I have x squared over x. That is top heavy. If something is top heavy, okay, I like to think of a celebrity that is top heavy. Now, I grew up in farm country. I grew up in the middle of nowhere. I listened to lots of country music. There's a country artist. Her name is Dolly Parton, and she is extremely top heavy. If you don't know who she is, go look her up later, not now. But she is extremely top heavy. Right? Is Dolly Parton really relevant anymore? Some people don't even know who she is. Okay, so because she's not relevant and no one knows who she is, there is no horizontal asymptote when the graph is top heavy. Now, your Algebra 2 teacher probably taught you that, but if there's no horizontal asymptote, there's this crazy thing called a slant asymptote. A slant asymptote is a dotted line that is slanted that your graph will get really close to, and it may cross, but it shapes the behavior of our graph. So a slant asymptote graph kind of looks like this, because that graph gets really close to that dotted slanted line and then runs away. So to find a slant asymptote, it's the linear result of the division. Now that's fancy math language. Linear result just means a line. That makes sense because it's a line. And of the division. If you think of division in this class, you should think of synthetic division. We just did that on our test. So we're going to synthetically divide this function up here. Now, on your test, you didn't have to change any numbers. But here, you want to divide by what's on the bottom. But you got to set that equal to 0 first. So if you set that equal to 0, you're really dividing by x equals -2 on the outside. And then take your coefficients from the top and put them on the inside. So 1, 10, -2. Drop the 1, multiply, add. Multiply, add. And now you're freaking out because you're like, Miss Schweitzer, we got a remainder. That can't happen. It happens every time now. Because if you divided and got a 0, that means it's a 0 of the function. This x plus 2 is not a 0 of the function, it's just the denominator. So for this unit, you should never, ever, ever get 0 for your remainder. If you get 0, you did something wrong. Now, if you keep reading down here in these notes, it says it's the result of division, ignoring the remainder. So ignore it. Then we started with x squared, so that means this guy has an x. So your answer is x plus 8, but it has to be a line. So throw back to math 8, y equals mx plus b. Hey, that y equals x plus 8 is your slant asymptote. It's a slanted line because it starts at 8 and then it goes up 1, right 1, up 1, right 1, because your slope is 1. So to find your slant, you do synthetic division. Now, I said that a graph can totally cross an asymptote. Okay, but 95% of the time, I will ask you, does the graph cross the horizontal or slant asymptote? And you will say no. 95% of the time, the answer to that question is no. So if you just want to write no in that blank and move on, that's fine with me. But you are mini mathematicians now. So I'm going to show you how to figure out if this graph crosses its asymptote. So to see if something crosses, in Algebra 2, you probably saw this picture on your SOL, and you had to tell it where those two graphs crossed or where they intersected. Okay, but if they gave you equations, now I'm making these equations up for my brain. If they gave you two equations, how would you find the solution? How would you find where they cross? You probably remember setting them equal to each other. So putting an equal in the middle. So in order to find if something intersects, you have to put an equal in the middle. Let me erase this crazy graph over here. So here, if I want to find out if my function, which is this random function they gave me here, crosses its asymptote, I have to set them equal to each other and see if they will be equal at any location in space. So what I'm going to do is I'm going to take the blue and I'm going to set it equal to the red. So I'm going to write x minus 2, or x squared over x minus 2 is equal to x plus 2. You don't need to include the y because that's what they're equal to, and we don't need that anymore. Now I have to solve for x. So it probably makes more sense to put this over 1 and cross multiply. 1 times x squared is x squared. Ooh, when I cross multiply here, I have x minus 2 times x plus 2. So I'm going to have to FOIL. And I'm going to go up here. I love this problem. This is fantastic. Okay, so I'm going to copy my x squared equals. Then x times x gives me x squared. X times 2 is 2x. Now that I distributed up, I'm going to distribute down. Negative 2x, negative 4. Something amazing happens. Those cancel. Woohoo, that's great. Now, I have x squared equals x squared minus 4. To solve for x, you want to bring all the x's to live together. So subtract x squared, subtract x squared. Those cancel. X squared minus x squared is 0. Does 0 equal negative 4? No, not ever. So this is no solution, which means this does not cross the HA or the SA, the horizontal asymptote or the slant asymptote. So the answer to the question, does it cross, is no, which I told you 95% of the time it will be. So if you want to avoid all of this terrible work, for when it says, does it cross, you can always write no, and 95% of the time you will be correct. And then at the bottom, this little tiny box is so important. Remember how to find x-intercepts from your test? Yeah, to find the x-intercepts, you set it equal to 0. But we already set the bottom equal to 0 for the vertical asymptote. So to find the x-intercepts, you set the top equal to 0. And that will tell you where the graph crosses the x-axis. Y-intercept is the same exact thing. You still substitute 0 for your x's. So, you have almost everything you need to start graphing. If you're not overwhelmed at this point, that means that you're doing a fantastic job. But if you're overwhelmed at this point, it's going to be okay. Okay, you have to be a beginner before you can be anything else. You have to try and you have to practice, and you're going to be just fine. It's a lot of steps, but you know how to do all of these steps already. Okay, so we have our last piece of information before we can start graphing. End behavior model. So, end behavior model goes with your horizontal asymptote. So what you're going to do is you're going to look at the same things we did for our horizontal asymptote. We're going to take the largest degree term divided by the largest degree term. Now that's fancy math language. So look for the highest exponents on the top and the bottom. If I actually divided x squared over x, I would get y equals x left over. That's my end behavior model, y equals x. And that means, wait, what picture does y equals x make? It makes a straight line. So that means the edges of my graph are going to look like the edges of a straight line. So on the left side, that graph is going to be going down. On the right side, that graph is going to be going up. And in the middle, it's going to do funky stuff. Okay, so we have to know what the edges are doing to draw our graph. Kind of like we did on polynomials unit, we put those arrows on the graph at the beginning. We're going to do similar things here so that we know where the edges are going. We can draw the graph correctly. Okay, so look at your highest exponent on the top and the bottom. If I divided x squared over x squared, I know there's a 3 and a 4 in the front. Ignore that for this. Okay? If you divided that, wouldn't your x squareds cancel? And if they did cancel, Your end behavior model is y equals c. Okay, the c doesn't stand for cancel, but it kind of makes sense. So if your x's will cancel, it's y equals c. Y equals c is just the generic form of like y equals a number, any number. So here, wouldn't we write y equals 3/4, like from the previous slide? Yeah, we would, and 3/4 is just a number. Y equals 3/4 is a horizontal line, so that means the end behavior of my graph is going to go left forever and right forever and do some funky stuff in the middle. The last one looks like it's bottom heavy to me. So that end behavior model right there, if you actually divided those x's, you would have nothing left on the top, and you would have an extra x on the bottom. So that end behavior model is y equals 1 over x. Yes, I know there's a 3 there. Okay, but we want the model, we want the generic version. We don't want specific numbers. So our end behavior model is going to look like y equals 1 over x. And you might not know this, but 1 over x makes this shape right here. So I know my edges are going to look exactly like that graph right there. Here are the steps for graphing a rational function, and they're the same exact steps as on your purple paper, but I wanted to summarize them again. So let's try one example together today, and then we'll try 3 million more examples when I am back on Monday. So for number 1, step 1, I can't see the box. I wish you were here to help me. Okay, for number 1, it says to factor. So you're going to factor the top and the bottom. So I'm going to go off to the side. For the top, I need numbers that multiply to -3 and add to +2. Guys, the only numbers that multiply to 3 are 3 and 1. Then I need them to add to +2, which means the bigger number must be positive. So my magic numbers are 3 and -1. That's for the top. It is fast factoring, so I can go x plus 3, x minus 1. For the bottom, I need numbers that would multiply to be 2. Stop right there. The only numbers that multiply to be 2 are 2 and 1. If they have to add to be -3, I need both of them to be negative so that they will multiply to positive, but still add to -3. So when I factor that, my magic numbers are -2 and -1. So I have x minus 2, x minus 1. Now, step 1 was factor. Step 2 is cancel. This is my favorite. Cancel that out. It's gone. It's dead forever. Okay, so how do you find the whole of the graph? It's from what cancels. But you have to take whatever cancels and set it equal to 0. So I know x equals 1, but a whole is a point. Is it there? Is it there? Is it there? Is it there? I don't know. I need to know the y value. So in order to find the whole, you have to substitute your x value back into your new formula. Your new formula is what's left over after you cancel. So my new formula is x plus 3 over x minus 2. Okay, that's my new formula that I'm going to substitute this 1 into to get the y value of the whole. I'm going to erase this factoring stuff so I have some space. When I substitute, I get 1 plus 3 over 1 minus 2, which is 4 over -1. So that's -4. Now I know where that is. And 1 -4 should be an open circle because it's a hole in your graph. That was step 2 and 3. Step 4 is find your vertical asymptote. Vertical asymptote should be the bottom of the graph set equal to 0, or the bottom of the equation, sorry. So x minus 2 equals 0. My vertical asymptote is at x equals 2. That's good because that's a vertical line where x is 2. Go draw that on your graph. We just set the bottom equal to 0, so to get your x-intercept, we have to take the top and set it equal to 0. So x plus 3 equals 0. X equals -3 is my x-intercept, but I really should write that as an ordered pair. -3, 0. That's a point. It's right there, so plot that. to get your y-intercept, you substitute 0 for all of your x's in your new formula right over here. So if I substitute 0 for my x's, aren't my x's just gone? So isn't it just the numbers at the back divided? Kind of like it was for polynomials, right? But now we have to divide them. So 3 divided by -2 will give me 3 over -2, but math people like to put the negative on the top. So I'm going to write -3 over 2. -3 over 2 is -1.5, so 0, so that's 0.5. 0, -1.5 would be right there. Now, to get your end behavior model, your horizontal asymptote, and your limits, you need to look at your x's. The things I just crossed out, now go look at them. Think, when you see ha, think like the funny story with the Kardashians and Dolly Parton. So, HA, is that top heavy, bottom heavy, or equal? It is equal because both of my x limits are 1. So when it's equal, you divide the numbers in the front. So your horizontal asymptote is y equals 1, because 1 divided by 1 will give you 1. This is a horizontal asymptote right there, so draw that in. The end behavior model is exactly what we just did. Okay, it's what happens with these x's right here. If I divided x over x, they would cancel. So your end behavior model is y equals c. If you have a horizontal asymptote, you can't have a slant. You can only have a slant asymptote when it's top heavy. So these two kind of go together. If you have one of them, you cannot have the other. This is what I was talking about before when it said crosses. To find if it crosses, if you want to guess no, 95% of the time you will be correct. But if you really want to know if it crosses, you need to take your function, which my new function that I'm working with is this one. So I need to take x plus 3 over x minus 2, and I need to set it equal to my horizontal asymptote, which is just a 1. I'm going to put it over 1 so I can cross multiply. And when I cross multiply, I get x plus 3 equals x minus 2. Now, right now, you should know that something weird is going to happen, because when you subtract x, they'll cancel. And you get 3 equals -2. So after all of that work, my answer is no, because 3 does not equal -2. I don't have an answer, so that does not cross. To get my limits, I really just need to look at what my graph looks like. So let's finish graphing this. Okay, to finish graphing this, we have to, first of all, connect our points together that we have. So, if I connect these points together, my graph is starting to look like this. This is good. On the left side, so when x is negative, what is y getting really close to but never touching? 1 is the correct answer. If it's getting close to 1 on the left side, it also has to be getting close to 1 on the right side. Okay, for a rational function, if one piece is on the bottom, on the left side, the other piece has to be opposite. It has to be on the top. So we know that piece has to be up at the top there, unless there's a weird x squared or something going on, which I'll show you later. But there's no x squared or anything, so that piece has to be on the top. As you go towards positive infinity, that graph is also getting close to the y value of 1 and never crossing. The last thing we have to write is our domain. Your domain is only interrupted by holes and your vertical asymptote. So our domain always starts at -infinity. So if I was like driving the car, I could totally drive, then I fall into a hole. Okay, so at what x value did I fall into that hole? At 1. So I have to stop at 1. And then miraculously, my car gets out of that hole and continues to drive from 1 until what x value is this wall located at? I run into a wall here. It's located at 2. Then miraculously, my car revives itself from running into the wall and jumps all the way up here. Okay, then I'm going to continue driving from 2 all the way to positive infinity. So you always start with negative, end with positive infinity, and you only stop at holes in your vertical axis. So I know that that was a lot, and I know that this is overwhelming, but your first unit was kind of like a warm-up. So this unit is a little bit scary, but you're mini mathematicians now, you can handle it. So I need you to do worksheet number 1. Number 1, 2, and 3 work together. My answers are posted on Google Classroom if you need them. And remember that I'm going to go over all of this again with more practice on Monday. Have a fantastic weekend.